There is a strange privilege built into our place in history, not because we are technologically advanced, not because we have reached some final stage of scientific understanding, but because the universe, at this particular moment, still allows us to ask questions that future civilizations may never even think to ask. Tonight, if you step outside and look up, the sky appears crowded with stars. Telescopes reveal something even larger. Beyond our own galaxy lie hundreds of billions of others, scattered across distances so immense that light has spent billions of years traveling before reaching Earth. Every faint galaxy is more than a destination. It is a message from another era. Together, those messages form a record of cosmic history stretching back almost to the beginning. It is tempting to believe that this view is permanent, that any intelligent species, no matter when it appears, would inherit the same evidence and reconstruct the same story. Current cosmology suggests otherwise. If the standard picture of an accelerating universe is broadly correct, then the observable cosmos is changing in a way that is almost impossible to notice over a human lifetime. Galaxy by galaxy, the evidence is slipping away, not exploding, not collapsing, simply drifting beyond the point where any signal can ever return. Distant galaxies continue to recede because space itself expands, and that expansion appears to be accelerating. Over unimaginable spans of time, more and more of the universe will disappear behind a cosmic horizon that no telescope can cross. Wikipedia. This is not a prediction about the destruction of the universe. The galaxies themselves continue to exist. Their stars continue to burn. Their planets continue to orbit. The loss is not physical existence. It is access. Imagine trying to write the history of Earth after every fossil had eroded away, every mountain had been flattened, every ocean basin erased, and every written record destroyed. The past would not become false. It would become unreachable. Cosmology faces a similar fate. Our understanding of the Big Bang depends on evidence that surrounds us today. We observe galaxies moving away from one another. We detect the faint afterglow of the early universe in the cosmic microwave background. We measure the abundance of the lightest elements formed within the first minutes after the Big Bang. Each line of evidence supports the others, creating a remarkably consistent picture of cosmic evolution. Yet none of these observations were guaranteed. They exist because we occupy a narrow interval in cosmic history where the universe is old enough to reveal its past, but not so old that the evidence has faded beyond detection. Researchers have even argued that, in the far future, observers inside a gravitationally bound galaxy could lose nearly every observational clue that led us to modern cosmology. Wikipedia. That possibility forces an uncomfortable question. What if scientific truth is sometimes limited not by intelligence, but by timing? We often imagine science as a steady climb toward complete knowledge. Better instruments replace older ones. New theories explain previous mysteries. Each generation inherits a larger map than the last. History encourages that confidence. Galileo's telescope transformed wandering points of light into worlds. Spectroscopy revealed that stars are built from the same elements found on Earth. Astronomy uncovered invisible regions of the universe. Space telescopes escaped Earth's atmosphere and opened entirely new wavelengths of observation. More recently, instruments such as the James Webb Space Telescope have pushed our view deeper into cosmic history, revealing galaxies that formed earlier and evolved more rapidly than many expected, forcing cosmologists to re-examine parts of their models rather than abandon them outright. Live science. Every major advance carried the same assumption. The universe is generous enough to leave evidence behind. But generosity has limits. The expansion of the universe does more than increase distance. It stretches light itself. Every photon traveling across intergalactic space arrives with its wavelength pulled longer than before. Over billions and trillions of years, ancient signals become so diluted that they fade beneath every practical threshold of detection. Eventually, even the oldest light remaining from the Big Bang may be redshifted beyond usefulness for observers living in that distant future. A Wikipedia. Those future astronomers would still possess mathematics. They would still understand gravity. They might master quantum theory far beyond anything we know today. Their instruments could exceed ours by unimaginable margins. Yet they could look into the heavens and discover something profoundly misleading. They might conclude that their galaxy is the entire universe. Without distant galaxies racing away, there would be no obvious evidence for cosmic expansion. Without a measurable cosmic microwave background, the earliest moments of the universe would leave almost no observational trace. The idea that everything began in a hot, dense state might seem unnecessary, even implausible. Their conclusions would not arise from ignorance. They would arise from missing evidence. That possibility changes the emotional center of cosmology. For decades, many of our greatest questions have focused on what remains hidden. Dark matter, dark energy, the origin of inflation, quantum gravity, the nature of consciousness. But there is another category of mystery that receives far less attention. Questions that become impossible because the universe itself quietly removes the clues. If that is true, then every observation we make today carries two kinds of value. The first is obvious. It helps explain reality. The second is harder to appreciate. It preserves information that may never exist again. Perhaps the greatest scientific archive is not stored inside observatories or data centers. Perhaps it is written into the sky itself, and the archive is slowly closing. Wikipedia, the first clue that our view of the universe is temporary came from a discovery that, at the time, seemed almost impossible to accept. When Edwin Hubble compared the distances to nearby galaxies with the way their light had shifted toward longer wavelengths, a pattern emerged. The farther away a galaxy was, the faster it appeared to be receding. It was not flying through space like shrapnel from an explosion. Space itself was expanding. That distinction matters because it changes what can eventually be observed. Expansion does not simply increase this distance between galaxies. It alters the relationship between time, light, and information. Every photon crossing intergalactic space must travel through a universe that continues to stretch beneath it. As that journey grows longer, the light arrives weaker, redder, and carrying less usable information than when it began. For billions of years, this process seemed manageable. Galaxies drifted apart, but their light still reached us. The observable universe continued to grow because ancient photons had enough time to arrive. Each generation of telescopes looked farther back than the last. Then another discovery complicated the picture. In the late 20th century, independent observations of disk-type supernovae suggested that cosmic expansion was not slowing under gravity as many expected. Instead, it appeared to be accelerating. The simplest model, consistent with those measurements, introduces a component now called dark energy. Although its physical nature remains uncertain, the name can create the wrong impression. Dark energy is not a glowing substance filling empty space. It is a label attached to an observed behavior. Something causes expansion to accelerate, but the underlying mechanism remains one of the largest unanswered problems in modern physics. For the purpose of this investigation, the cause is almost secondary. The consequence is what matters. Acceleration means there are regions of the universe that will eventually move beyond any possibility of communication. Not because they exceed the speed of light through space in the ordinary sense, but because the expansion of space prevents new light emitted there from ever overcoming the growing distance between us. A useful analogy is an ant trying to walk across an endlessly stretching rubber band. The ant never stops moving. Its speed never changes. Yet the surface beneath it stretches so rapidly that the destination continues to recede faster than progress can be made. Eventually, reaching the other side becomes mathematically impossible.
something similar happens to information carried by light. This introduces a boundary, unlike any horizon we experience on Earth.
A mountain blocks vision because it is in the way. Climb higher, and the horizon changes. A cosmological horizon is different. No improvement in engineering can overcome it. No larger telescope can collect photons that never arrive. No detector can measure signals that the expanding geometry of space-time permanently removes from causal contact. That is why future cosmology may face a limitation that has nothing to do with intelligence. Imagine a civilization appearing 100 trillion years from now. Its scientists might possess computers that make ours appear primitive. Their understanding of particle physics could be astonishingly complete. They may solve engineering problems that we cannot even formulate. Yet when they build observatories and examine the night sky, almost every galaxy beyond their own local gravitational group may already have vanished from view. Not destroyed, simply unreachable. The local group, bound together by gravity, is expected to remain intact, even as the rest of the universe recedes beyond the observable horizon. To those distant observers, their galactic neighborhood could appear to be all that exists. The implications spread further. Today, one of the strongest pieces of evidence supporting the Big Bang is the cosmic microwave background. It surrounds us in every direction, a relic from a time roughly 380 years after the universe became transparent enough for light to travel freely. It is often described as an afterglow, but even afterglows fade. As the universe expands, those ancient photons continue to lose energy. Their wavelengths stretch farther and farther until the signal becomes extraordinarily difficult to distinguish from other sources of radiation. Several theoretical studies have suggested that, in the remote future, this background could become effectively undetectable within any realistic experiment. If that happens, an entire chapter of cosmic history disappears from observation. Future astronomers would not reject the Big Bang because they had disproved it. They might never invent it in the first place. From their perspective, there would be no compelling evidence demanding such a beginning. That possibility exposes an assumption hidden beneath much of scientific thinking. We often believe that enough intelligence inevitably produces the correct picture of reality. The universe may not work that way. Knowledge depends on evidence. Evidence depends on what nature allows to remain observable. And observability is not constant across cosmic time. This changes how we should think about our own era. The modern age of astronomy is usually described as the beginning of a long ascent. Bigger telescopes, better detectors, larger surveys, more precise measurements. That description is true, but it is only climbing. We may also be racing a clock that started long before Earth existed. Every new observation is made inside a window that slowly narrows. The unsettling possibility is that we did not choose this window. We simply happened to awaken while it was still open. The next question is even more difficult.
If the universe can erase evidence of its own past,
what else might already have been lost long before humanity ever looked up? Long before there were galaxies, stars, or planets, the universe carried almost no visible structure. Matter was distributed with astonishing uniformity. Tiny fluctuations existed, but they were so small that they could only be detected after the invention of sensitive microwave observatories. Those minute differences eventually became everything we see today. Every galaxy cluster, every black hole, every planetary system, including our own, grew from those faint irregularities. This origin story is not something we inferred from philosophy. It emerged because several independent observations point toward the same conclusion. The expansion of the universe, the cosmic microwave background, and the distribution of galaxies all reinforce one another. None of these observations alone tells the full story. Together, they create a framework that has survived decades of increasingly precise measurements. That is one reason modern cosmology has become so successful. It does not rely on a single extraordinary discovery. It relies on many ordinary observations, agreeing with one another. But what happens when those observations slowly disappear? Consider how science normally corrects itself. When astronomers encounter an unexpected result, they rarely abandon an existing theory immediately. They search for additional evidence. They compare observations made using different techniques. They ask whether an anomaly is instrumental, statistical, or genuinely physical. The strength of science lies in redundancy. Nature leaves multiple fingerprints. Yet redundancy itself depends on those fingerprints surviving. Suppose the distant future removes one line of evidence after another. First, galaxies outside the local group become inaccessible. Then the relic radiation from the early universe fades below detection. Eventually, the large-scale structure that once revealed billions of years of cosmic evolution can no longer be mapped. Future observers would still have stars. They would still witness stellar birth and death. They would understand nuclear fusion. They could calculate the life cycles of suns with extraordinary precision. What they would lack is context. Imagine finding a single page torn from the middle of an enormous history book. The language is perfectly readable. The events on that page are internally consistent. Yet the opening chapters and the ending are gone. No matter how intelligent the reader becomes, reconstructing the missing narrative eventually requires guesswork. Cosmology may face the same limitation. The unsettling implication is that our current picture of the universe depends not only on human curiosity, but on the extraordinary good fortune of living while enough evidence remains. Astronomers sometimes refer to this as an observational epoch. Not every epoch offers the same opportunities. There was a time before heavy elements existed, when rocky planets could not form. There will likely be a time after most stars have exhausted their fuel. Our own era sits between those extremes, old enough for cosmic history to leave measurable traces, young enough that those traces have not yet vanished. That realization changes the meaning of discovery. When the James Webb Space Telescope observes galaxies from the first few 100 million years after the Big Bang, it is not merely extending humanity's vision deeper into space. Because light requires time to travel, it is preserving observations of a period that will never become easier to study. Every improvement in sensitivity is also an act of historical preservation. The farther we look, the older the archive becomes. And archives are fragile. There is another consequence that receives far less attention. Science often assumes that later civilizations inherit greater knowledge because they inherit better technology. That assumption is reasonable on Earth. Each generation benefits from the accumulated work of those before it. The universe, however, is not obligated to preserve the evidence those generations need. Technology cannot observe information that no longer reaches the observer. There is no engineering solution for a photon that never arrives. This is one of the rare cases where physical law imposes a permanent boundary rather than a temporary technical challenge. It also forces us to reconsider a familiar image. We often picture scientific progress as a straight road leading steadily forward, but perhaps it resembles close climb surrounded by rising fog. The climbers become stronger. Their instruments become sharper, their maps improve. Yet, beyond a certain point, the landscape itself begins to disappear because the mountain is changing while they climb. The possibility sounds almost unfair. Future civilizations may solve problems that seem impossible to us, while remaining permanently unable to answer questions that schoolchildren can discuss today. Not through negligence, not through lack of imagination, simply because the universe no longer provides the necessary evidence. That idea introduces a profound shift in perspective. Perhaps ignorance is not always the absence of knowledge. Sometimes it is the inevitable consequence of living too late. If that is true, then our greatest responsibility is larger than making new discoveries. It is preserving the evidence while the universe still permits us to see it, because the next generation may inherit our data. But the civilization born 1 trillion years from now may inherit only our conclusions. And without the sky that allowed those conclusions to be tested, even the most careful records could begin to look less like science and more like mythology. That possibility raises an uncomfortable question. If the universe has already hidden parts of its own history from future observers, could it also have hidden parts of its history from us? There is a quiet assumption beneath nearly every scientific discovery we celebrate. If we ask the right questions and build instruments with enough precision, nature will eventually answer. For most of modern science, that assumption has worked remarkably well. When Neptune's orbit refused to behave exactly as Newton's equations predicted, astronomers searched for another planet. They found one. When Mercury's orbit resisted every conventional explanation, Einstein's theory of general relativity accounted for the discrepancy. Again and again, better observations resolved deeper mysteries. That history encourages optimism. But cosmology occupies an unusual position among the sciences. Most sciences can repeat experiments. Astronomy rarely can. Cosmology cannot. There is only one observable universe. We cannot prepare another one under different conditions. We cannot rewind cosmic history and watch it unfold again. Every conclusion rests on whatever evidence the universe has chosen to leave behind. That limitation becomes increasingly significant as evidence disappears. Imagine trying to reconstruct the history of an ancient civilization after nearly every city has collapsed, every document has decayed, and every monument has eroded into dust. Archaeologists could still recover fragments. From those fragments, they might infer an entire civilization. But they would never know how many crucial pieces had already vanished before the excavation even began. Modern cosmologists face a similar uncertainty. We often describe the observable universe as though it represents reality itself. It does not. It represents only the portion from which light has had enough time to reach us. Everything beyond that horizon remains physically real under our current understanding of cosmology, but observationally inaccessible. Even today, we are already surrounded by limits. The cosmic microwave background forms one of them. Before the universe became transparent, roughly 380,000 years after the Big Bang, light scattered continuously through a hot plasma. No optical telescope, regardless of size, can directly image anything earlier using ordinary light. Our earliest visual record begins there. Everything before that must be reconstructed indirectly through particle physics, gravitational theory, and increasingly sophisticated observations that search for subtle signatures left behind. Even our current beginning is not truly the beginning. It is the earliest chapter that light still allows us to read. That distinction is easy to overlook because our observational window is extraordinarily rich. The universe appears generous. Galaxies fill every deep field image. Background radiation surrounds us. Large-scale structures stretch across hundreds of millions of light years. Patterns emerge almost everywhere we measure, yet generosity is not permanence. As acceleration continues, those patterns slowly unravel, not because the universe becomes simpler, but because its evidence becomes increasingly fragmented. Future observers may inherit a sky that appears internally consistent, while hiding almost everything necessary to explain how it came to exist. That possibility forces an uncomfortable comparison with human history. Entire civilizations have vanished because their records were lost. Languages disappeared before anyone documented them. Libraries burned. Cultures dissolved into scattered artifacts that survive only by chance. Historians know that absence of evidence is not evidence of absence. Sometimes history becomes invisible. The universe may follow the same rule. Not every missing clue reflects a failure of investigation. Sometimes the clue itself no longer exists within observational reach. This perspective also changes how we think about technological progress. There is a tendency to imagine that every scientific frontier eventually yields to more powerful instruments. Build a larger telescope, launch a more sensitive detector, collect more data. Repeat. That strategy has transformed astronomy for more than a century. But cosmological horizons introduce something different. No telescope can detect photons that expansion permanently prevents from arriving. No computational breakthrough restores information that never enters the observable universe. No artificial intelligence, regardless of sophistication, can infer unlimited truth from permanently incomplete evidence. Computation can extract more from data. It cannot create observations that physical law forbids. In other words, the ultimate limit on knowledge may not be intelligence. It may be access. This possibility has profound implications for how humanity should think about the present. We'll often describe ourselves as living in the infancy of scientific civilization. Compared with what may come over the next million years, that description is probably accurate. Yet with respect to cosmology, infancy may coincide with opportunity. Our descendants may become vastly more intelligent. Their technology may exceed ours beyond recognition, and still they may envy something we possess, almost accidentally. A sky that still remembers. Every galaxy we catalog, every background photon we measure, every spectrum recorded by today's observatories, may become part of an archive that future civilizations cannot independently verify. That does not diminish future science. It elevates the importance of our own, because preserving evidence is not merely preserving data. It is preserving the possibility of asking questions that the universe itself may eventually erase. The unsettling thought is not that the cosmos is becoming darker. It is that darkness changes what can be known. And if the observable universe has an expiration date, then perhaps knowledge itself has one as well, not absolute knowledge, but knowledge of origins. The final question is no longer whether the universe is expanding beyond our reach. The measurements strongly suggest that it is. The deeper question is whether we are living during the only era when the universe is still capable of explaining itself. There is a temptation, whenever we confront a limit like this, to assume that another breakthrough will eventually remove it. History encourages that instinct. Every generation has mistaken its own horizon for the edge of reality. The naked eye gave way to telescopes. Optical astronomy expanded into radio, infrared X-ray, and gravitational wave observatories. Each new instrument exposed a universe that had been present all along, waiting for the right way to observe it. So it is reasonable to ask whether the cosmological horizon is simply another temporary barrier. Could some future technology allow information to outrun expansion itself? Current physics offers little reason to expect that. General relativity places a fundamental distinction between traveling through space and the expansion of space. The recession of extremely distant galaxies is not caused by those galaxies accelerating through the universe like spacecraft. Instead, the geometry separating us changes over time. That difference matters because it prevents a simple engineering solution. Building a faster telescope is meaningless. A larger mirror cannot collect photons that never arrive. Even if an observer could survive for trillions of years, patience alone would not solve the problem. Waiting longer does not reveal more of the universe. Once accelerating expansion permanently removes regions from causal contact. Some frontiers shrink instead of growing. That realization forces us to examine an assumption buried inside one of humanity's oldest ambitions. Since the earliest civilizations, people have believed that ignorance is temporary. The stars seemed mysterious until mathematics described their motion. Lightning appeared supernatural until electricity explained it. Disease looked like fate until biology uncovered invisible organisms. Again and again, mysteries yielded to investigation. Cosmology reminds us that this pattern may not continue forever. Some questions disappear before they can be answered. Others become impossible because nature erases the evidence needed to distinguish competing explanations. The distinction is subtle but profound. There is a difference between not knowing and no longer being able to know. Philosophers have wrestled with this distinction for centuries, but cosmology gives it physical form. Imagine two civilizations separated by 1 trillion years. The first observes thousands of galaxies beyond its own. The second sees only one. Both follow identical scientific methods. Both reject unsupported claims. Both insist on evidence. The first concludes that the universe began in a hot, dense state and has expanded for billions of years. The second finds no convincing observational reason to accept such a beginning. Which civilization is more rational? Neither. Each is faithfully interpreting the evidence available to it. Their disagreement would not arise from intelligence or culture. It would arise from history. The universe itself would have changed the experiment. That possibility transforms our understanding of scientific progress. Progress is often imagined as an arrow pointing in one direction, toward greater certainty, toward deeper truth. But perhaps cosmology resembles a tide. For a time, the water recedes, revealing structures hidden beneath the surface. Then, slowly and inevitably, the tide returns. Nothing beneath the water has vanished. Only our ability to see it. That image carries another implication. Our era may represent an unusually transparent interval in cosmic history. Not the beginning, not the end. A brief period when multiple lines of evidence overlap just enough to reconstruct events, stretching back nearly 14 billion years. We rarely appreciate how extraordinary that overlap is. The oldest light is still visible. The expansion of galaxies is still measurable. The chemical fingerprints of primordial nucleosynthesis remain detectable. Large-scale cosmic structures have not yet disappeared beyond observation. Each of these clues reinforces the others. Remove one, and cosmology becomes harder. Remove several, and entirely different models could appear equally reasonable. This is why modern astronomical surveys matter in ways that extend beyond their immediate discoveries. Projects that map millions of galaxies or measure tiny fluctuations in relic radiation are not simply refining decimal places. They are preserving observations from a universe that will not always be observable in its current form. Future civilizations may inherit databases of astonishing precision, if those archives survive. But data alone presents its own challenge. Scientific evidence derives its strength from independent verification. If the original sky can no longer be observed, future researchers may be forced to trust records that cannot be reproduced directly. That would represent an unusual moment in the history of science, not because the evidence became weaker, but because reality itself stopped offering fresh confirmation. The universe would have transformed repeatable observation into historical testimony. And history, however carefully preserved, is always more vulnerable than direct experience. Which leads to one final possibility. Perhaps we have been asking the wrong question all along. Instead of asking whether humanity will eventually understand everything, perhaps we should ask whether everything is even available to be understood. Because if knowledge depends on evidence, and evidence depends on timing, then our greatest scientific achievement may not be discovering the history of the universe. It may be discovering it before the universe quietly closes the record forever. There is an old idea that every generation believes it is living at a special moment in history. Usually, that belief does not survive careful examination. Most centuries are not uniquely privileged. Most discoveries eventually become stepping stones toward larger ones. The people making them rarely understand how small their contribution will appear from the perspective of the future. Cosmology may be one of the few exceptions. Not because our theories are complete. They are not. Dark matter remains unidentified. Dark energy is still understood only through its effects. The earliest fraction of a second after the Big Bang remains beyond direct observation. Quantum gravity has resisted every attempt at experimental confirmation. Some of the largest questions in physics remain unanswered, yet none of those uncertainty erase an extraordinary fact. We can still see enough of the universe to know that these exist, that if intelligent observers emerge tens or hundreds of trillions of years from now, they may possess a deeper understanding of matter than we do today. They may manipulate space-time in ways we cannot imagine. Their mathematics could reveal structures hidden from our current theories. But no amount of intelligence can recreate observations that the universe itself has erased. There is an uncomfortable asymmetry here. We often measure civilizations by their technological achievements. Perhaps we should also measure them by the quality of the sky they inherit. Humanity did not earn this sky. We happened to appear while the oldest light still crossed the cosmos, while distant galaxies still carried measurable histories, while the expansion of the universe remained visible rather than inferred, while enough independent clues survived to weave together a coherent account of nearly 14 billion years. That circumstance is neither a triumph nor a guarantee. It is an opportunity, one that places an unusual responsibility on our species. Every astronomical survey completed today becomes more than a scientific project. Every spectrum recorded from a distant galaxy, every precise map of the cosmic microwave background, every measurement of gravitational waves, every catalog of large-scale cosmic structure is an attempt to preserve evidence that later observers may never collect again. The archive matters because the sky itself is not permanent, and yet even that archive has limits. Suppose humanity survives for millions of years. Suppose our descendants protect every observation ever made. Suppose no data is lost. Would that mean they understand the universe as directly as we do? Not entirely. Science depends on more than records. It depends on the ability to challenge them, to repeat observations, to discover unexpected details hidden within familiar measurements. If future astronomers cannot compare ancient data against the living sky, then part of science quietly changes. Observation becomes inheritance. Verification becomes interpretation. Their confidence may rest increasingly on the work of civilizations long gone. That possibility turns our usual perspective upside down. We often imagine ourselves passing incomplete knowledge forward to wiser descendants. Perhaps in cosmology, we are also passing forward opportunities they will never receive. The universe is not simply expanding. It is editing its own history, not by changing the past, by limiting who can still observe it. There is no malice in this process, no intention, no design, only the steady consequence of physical law unfolding across incomprehensible spans of time. Perhaps that is the deepest source of unease. The universe does not hide its history because it wishes to remain mysterious. It hides its history because it continues to evolve. Every passing billion years rewrites what can be known. Every receding galaxy reduces the number of witnesses. Every fading photon narrows the conversation between the present and the beginning. When we ask whether humanity is alone, whether the universe has a purpose, whether intelligence has a future, we often assume those are the greatest questions available to us. There may be another. How many questions can only be asked during this brief moment in cosmic history? We cannot know. By definition, the questions already erased have left no trace. Perhaps countless chapters of reality disappeared long before Earth formed. Perhaps future civilizations will lose chapters that still surround us tonight. Knowledge, then, is not only a product of curiosity, it is also a product of timing. The sky above us is more than a collection of distant lights. It is a temporary record. A record written across expanding space carried by ancient photons, and preserved only because they have reached us before the universe carried them beyond every possible horizon. One day, that record will close. Not with an explosion. Not with a final signal. Simply with fewer pages remaining visible. And if that future arrives
exactly as current evidence suggests,
then the greatest privilege are that we can observe the universe. It is that, for a fleeting moment between its beginning and its unimaginably distant future, the universe still remembers enough of its own past to explain where it came from.